Welcome back. And the topic today is to try to wrap up a little bit discussion about variational autoencoders with a little bit more mathematics. And then I also wanted to discuss project 2. The mathematics today is going to be a continuation, and that's partly a repetition from last week. And then we're going to point to how these things are actually encoded. So variational autoencoder is extremely popular and is one of the methods which is widely used as a generative method. And it paves the ground also for so-called diffusion models, so variational diffusion models, as they are called. And this is something which we will look at next week. Today, if we get time, I will say something about the general adversarial networks as well. Although I would say that the focus nowadays is much more on diffusion model and also on the variational autoencoders. And the variational autoencoders contain a lot of this kind of nice mathematics which we like to see. I wanted also to say something about the project. So you probably see now I put a deadline for June the 7th. You can collaborate as much as you want. There are groups who have decided to make one project. So for those groups, please feel free to continue as you've been doing. So there's no need to change your plans. Now, for those of you who would like to jump into a new topic, you can obviously define something yourself. So just discuss with us, and then we can see whether this is relevant or not. Alternatively, if you look at the project descriptions, which we have online here, so we would like you, and this applies also for those of you who make one long project, to actually try to write everything as a scientific report. And we've put up some instructions on both the way we do the evaluation, but also there is a very nice link to a talk by Anne Grumi on writing abstracts. And this is actually called Writing Efficient Abstracts and Good Titles. So she's actually an editor of one of the European physics journals, and she has a long experience on actually looking at scientific articles which are sent into scientific journals, but also writing scientific articles. And so if you want some hints and tips on how to write a good abstract and a good title, take a look at the slides which we have on the writing abstracts here. Then we also have a file here on evaluation and grading, and you can typically see the way we want you to prepare the report. So for those of you who did the first project, we were a little bit lax with the way you write the report. But if you write a second project, or you just have one unique one, we want you to take a look at how you write a scientific report. For some of you, this is pretty boring because you've already written scientific articles and reports and so on. But in case you have not, take a look at these pages. And for those of you who have taken other project-based courses, I mean, it's very much the same way we evaluate projects here as we've been doing in previous courses. So typically the report should have an abstract, it should have an introduction, there should be a conclusion with perspectives, description of the methods, description of the codes you have developed. And we also want to run the codes so that we know that this is something you have done and developed, so we can test it and that it works. But these are things which most of you are familiar with. And there's also at the end, you can choose whether you want to look at the markdown file or the HTML or the PDF, that's up to you. At the end, there is also a grading scheme, so how we actually put in the grades. And for those of you doing the PhD variant of this course, I mean, the grading is pretty simple. It's either passed or not passed. And that means either a B or A, which is the final grade. And for those of you who are taking the master degree variant, then it's a normal letter grade. Just let me know if there are things which are unclear. So I just wanted to go a little bit back to the project. So for those of you who plan to write a second project, we actually have some suggestions, unless you have defined something different. This is fully possible. But then we would like you to focus on one or perhaps two of the methods which we have been discussing. So we paid a lot of attention on Boltzmann machines, and then we also been discussing variational autoencoders in quite some depth. You can choose then the kind of path you want. So you can have a computational path, and there you can actually, if you want to, like some people have actually been writing a code for CNNs, but that's if you write a code for CNNs, or if you do a code for RNNs with long short-term memories, this is something which we view more as a full semester project, because that's quite demanding. But if you want to write a code for, let's say, Boltzmann machines, this is something which can be done in the span of something like the time we have at our disposal till June the 7th. So in that case, you could choose to write just a code for Boltzmann machines and implement that. There are several examples in PyTorch, which I put online, which you could borrow and just use. And then you can make it more flexible, you can make it more object-oriented, etc. There is a differential equation path, as we had before, for variational autoencoders. Then you would typically use existing software from PyTorch or from TensorFlow or similar libraries, and then tailor that to the solution of, let's say, differential equations. So this is something you can explore. If you look at that computational path, the data you could implement it on could be data of your own choice, or you could just use the MNIST data, which we have been using through the lectures. So in the lectures, I am not being very fancy when it comes to data sets, and that's simply because the MNIST is become a kind of benchmark data in all textbooks. So if you're presenting a new method, it's like when you do a high-performance computing and you are presenting a new linear algebra method, and you want to run this on high-performance computing facilities, then you have existing benchmarks which you're comparing that with. And in machine learning, it's normally the MNIST data, or if you want to be a little bit more fancy, you have the fashion MNIST data, which is actually images of different dresses, trousers, T-shirts, or whatever. So I see we have some noise in the background here. So let me just, no, okay. So the third variant is a variational autoencoders with Bayesian machine learning. And I know that some of you wanted to follow that path. And there is actually a pretty nice library which you can access online, where they've been testing variational autoencoders together with Bayesian machine learning. So today, when we are bringing back the variational autoencoder theory, we're actually going to remind you of Bayesian statistics. So this is more tailored to those of you who would like to explore that path as well. There is also an option, which I didn't put in here, because I know that somebody is also taking a course we have on quantum computing. And one of the possibilities then is actually to write a second project for both this course and the Physics 5419, where you would study Boltzmann machines and quantum Boltzmann machines. And there is also quite some hype on quantum variational autoencoders, because these are methods which have a natural propagation into quantum computing. So for those of you who have an interest in that, there is a possibility, which I didn't list here, to actually bring together the projects from these two courses and just hand in one single project. And that will be accepted for both courses, because it's a little bit more demanding if you want to add the quantum computing aspect as well. Any questions to the projects? So feel free also to use these methods if you have what I call the data path, and you have some data you want to analyze with variational autoencoders, with Boltzmann machines or diffusion models. and you have, let's say, a classification problem from your own research, and you want to apply these methods to the data sets, and then compare with what you perhaps did in project number one. This is another alternative. So I hope there is enough flexibility so you can actually do what your heart wants you to do, actually. That's a very important aspect, okay? Questions? So, okay. Else, the rest of the project file, which you see here, is basically much the same. But if you're interested in variational autoencoders, there's an article here which we will refer a lot to today. And that is the article by Kim and Welling. These are the people who introduced variational autoencoder. And they have actually written a very pedagogical article from 2019. There is correspondingly a similar article by Calvin Luer, which it also gives you a very pedagogical introduction to variational autoencoders and diffusion models. So take a look at these two, because in the lectures which I made last week and this week, I've been borrowing a lot from these two articles. And they're actually very good reads. So many textbooks. And if you go back to the textbook by Goodfellow et al., which came out in 2016, that textbook doesn't go very much in the depth of variational autoencoders. So it merely lists just the basic equations. And when you read those chapters, you are a little bit at loss when you look at them. Okay. So if there are no questions, I'm going to jump into the finalization of the topic this week. And these are just some wordings which I borrowed from Kingma and Welling in this article here. And this is about why general modeling is attractive, generative modeling. And so I'm just repeating some of the basic motivation for why we are looking at generative modeling. And as you know, I mean, basically everything you've been doing now with ChatGPT is based on this. And for somebody who comes from the physical sciences, like geoscience, chemistry, physics, you can actually express physical laws and constraints in the generative process. And that's extremely interesting. This is very much like, for those of you who are doing physics informed machine learning, you also can actually bake in constraints like boundary conditions in partial differential equations in the training of a neural networks. While like here, details that we don't care about, we don't know or care about, they are treated as noise. And that's a way to take out degrees of freedom, which we don't think of relevant. And the resulting models are usually highly intuitive, and you can interpret them. So when you extract a probability distribution, like a Gaussian, is something which we can interpret easily, right? And when you have a probability distribution, you make the plot, you can always make interpretations of what this may mean, because it gives you the probability of finding something. So generative models, as we've been discussing, generate a probability distributions. And that is something which can lead to models which are a little bit more interpretable. And then you can test against observations. We can confirm or reject our theories about how things are working. And another reason for trying to understand the generative process of data is that it naturally expresses causal relations of the world. So it's time a little bit to think of the kind of machine learning methods which we have been exposed to. So if you think of a standard feed-forward neural network, which we refer to as a discriminative model, these are models which, one, they allow you to fit the data, and then with the fit, you can make a prediction. So that means that you can say that you should get this result given a function you've been fitting. And you can find correlations in the data set. However, a standard discriminative method like a deep learning method or like a CNN or a normal neural network, or more the ancient methods like decision trees, linear regression, and so on, they don't give you a causal interpretation. That means given A, what is the probability of finding B? So when you have a probability distribution, you can actually say, given A, what is the probability for B? And the other thing, when you have a probability distribution, you can also estimate the errors. You can calculate the standard deviations. You can give an estimate of the parameters and how good they are and how bad they are, etc. So in a sense, generative models give us everything. They give us the capability to make predictions, the capability to find correlations in the data sets, the capability to have something which obeys causality. And finally, you can quantify the errors. So in a certain sense, for us doing natural science or the physical sciences, this is actually much more interesting than just being able to fit some data with a neural network. And as I say here, causal relations have the great advantage that they generalize much better to new situations than you just having found correlations in a given data set. Like if you fit housing prices, you find that there's some data correlated and some are not. The number of rooms is most likely correlated with the price of the house, which is pretty obvious. But then the correlations you find are given by that data set. Now you can actually generate new data sets. And once you understand the generative process of an earthquake, you can use that knowledge in different countries. So I would say that generative modeling is actually where we are moving, and it's much more interesting, and it combines all these features of Bayesian statistics with much of the benefits of machine learning and the training of machine learning. So let's remind ourselves a little bit of what these variational autoencoders are. And I'm going back to the whiteboard. So let's do that. So just a quick reminder of things which we are doing. And I wanted to give you first a quick reminder on traditional autoencoders, which we discussed in before the Easter break. So a traditional encoder or autoencoder, so let's just remind ourselves about that. And these are also methods which you could explore in the second project if you want to. So in the traditional autoencoder, what we had was some data which we define as observations. And then this data was sent into a function f, and that function produced a reduction of the data set. So we could think of this encoder part. So this is the encoder. And then we had something which are called either hidden or latent variables. So I will often refer to them either as hidden or latent. And we call this for an H. And then you have a function which de-encodes the data you have. And you can reduce the dimensionality like we discussed before the Easter break when it came to principal component analysis. So this H is normally given by some function f with x as an input, and it has some parameters, which we could call phi. Then these data are sent into a new function, which we call for a decoder. And that would be given by a function g, and that produces a final output x. And what we did then was to typically have a minimization problem. So where we would minimize argmin, and there would be a function which now gives us x tilde, which is given in terms of this g as a function of h, and then it has some parameters which we call theta. And we would then optimize everything with respect to phi and theta. And then one of the typical functions which we would evaluate would be the norm 2 of the difference between x and x tilde. And one of the things we discussed before the Easter break was that these traditional autoencoders, they could be you could actually show that they correspond to a dimensionality reduction. And if you had a linear dependence in terms of these parameters phi and theta, you could show that that corresponded exactly to the classical principal component analysis as a dimensionality reduction method. So these H's are normally meant to reduce the dimensionality of the problem. And then you decode them, and hopefully you get out something which is close to the variables which you plugged in. And in the traditional autoencoder family of methods, these functions f and g are normally different types of deep learning networks. It could be a standard feed-forward neural network, it could be a convolutional neural network or recurrent neural network, etc. So if these are methods you would want to explore, then we should do that. Now, in this specific case with autoencoders, we are not producing a probability distribution. So what we are interested in generative methods, so I'm just repeating some of the mathematics here so that it's a little bit easier to see the basic connections and how we can program a variational autoencoder ourselves. Because the equations we are going to get at the end, where we used last week the Kullback-Leibler divergence, which I'm going to remind you of, when you look at the equations you have, it's not easy to see how you could code them in a straightforward way. So we have to make approximations. But we are interested in a probability of P of X of some parameters theta. And I'm going to rewrite this one as a P of X, no, P of theta of X. So we want to generate that. And this is something which we call the marginal probability. And this is this is a theta actually. So let me just try to rewrite this one a little bit better. So I'm going to use this kind of notation, and X can be a vector, it can be a matrix. So we're just leaving that unspecified. And what we want to is actually to find a probability which is as close as possible to the probability which determines the data. So what we want, so the true probability could be something which we call P star of X. Suppose that exists, but we don't know it. So what we want is actually that this P of theta of X is as close as possible to this real probability or the true probability. We may not know that. So we're also interested in something which is called the conditional probability. Often also interested, and this is where the decoder encoder part comes in variational autoencoders. In the conditional probabilities, so just to remind you, this is the marginal probability, and then we have the conditional probability. And this is a conditional probability for some theta of y given x. But then we would also be, or we may be interested in a probability of x given y. What we did last time was actually, in our case, we defined this latent variables. This y is going to be replaced by h, which we call the latent or hidden variables. So you could think of these in terms of a Boltzmann machine, where the Boltzmann machine refers explicitly to the hidden nodes as degrees of freedom. So where do we want to go? So the basic structure of an autoencoder, a variational one. So I want of a variational autoencoder is now something like this. And it's going to be different from the standard autoencoder. So we are going to have something which we are going to call obviously the input data. So this is our data set, X. So this is now fed in to our machinery. And then from this, we're actually going to produce an encoder, which now brings us over to the latent space. So up here, we have a latent space. So this is an encoder. And we are going to define a conditional probability, which now brings us into this space. And we are going to define that as a function Q with some parameters phi of H given X, so which is our input. So that's the X here, okay? So think back to the traditional encoder. So the traditional autoencoder, we had a function F, which then translates the input to some latent variable H. And this gives us a specific dimensionality reduction here. And that's given by this function F as function of these parameters theta, which we are going to optimize. So if you look at the autoencoder, the variational one, the difference now is that instead of having such a function F, which could have been a neural network, we are now defining a conditional probability for generating these H's. Now, this goes into the latent space, and in this latent space for H, this is variable H, there's going to be a probability distribution, which we call for a P of theta of H. And I'm using this now to bring back Bayes' theorem, because variational autoencoders are us playing around with Bayes' theorem. So what happens next then is when we have these probabilities, we then go back, and then we have the decoder part. And in this decoder part, we have new parameters theta, and there is an X given H. So we have a given H, and then we produce an X with a given H from this latent space. So this is a decoder part, and this brings us back here. And then we can compare the X we produce here with the original input. So this is the encoding and decoding part. But now we need to bring back Bayes' theorem because that plays a central role. So I'm going to repeat a little bit some of the elements here. So I hope you don't get offended if I do that. But to see how the variational autoencoder is set up is something which I think is a little bit important, and that's why I'm bringing in these various elements of repetition, because everything which we do here is linked with Bayes' theorem. So let's bring back Bayes' theorem before we move on, and we're going to set up the equations which we need to program. So let me quickly remind you of Bayes' theorem. I think it's written with the, I think it's written like this. So we know that the standard product rule from probabilities, so we have a P of X of H is given by P of X given H multiplied with the probability of H. So in the literature, this is normally called the prior, and this is called the likelihood. So we have a model for it. And this is again the same as us having H of X multiplied with P of X. So these are two equivalent statements. And if you take a course in statistics, these statements are normally proven. So now we're just taking them as they are. And this is the probability, this quantity here, for finding X and H. Okay, so Bayes' theorem simply states that we can now combine these two equations, and we can find the following equation. So Bayes' theorem combines these two equations, combines these two equations so that you can find one of these conditional probabilities given the other. So that means that you can then have a P of, let's say, H given X, which is now simply P of X given H, and then multiply with P of H, and then divided by P of X, or you can interchange the two. So the probability which you have here is normally called the posterior probability. And this would be normally just called the likelihood, and this is called the prior. And these are often probabilities which you define a model. So you have a belief in a specific model. Now for variational autoencoders, the standard approach is to set one of these, and also this one, to be a Gaussian distribution. And you will see the basic machinery when we come later, when we just repeat some of the things we went through last week. So this is one of the alternatives. Alternatively, you can just switch these equations and find a similar equation for X given H. And in that case, you would have PH given X multiplied with P of X divided with P of H. So this quantity you have here normally is called the marginal probability, and it serves also as a way to normalize the full posterior probability. Any questions so far? Okay, so these are just some basic definitions. Now, the thing which we want is actually this probability P of theta or X. So this is the final which we want. So when we look at the variational autoencoder, at the end, what we want now is a probability. The final product is P theta of X, which we want to train with the data set which we have. So you could then, the data set could be an image which you're feeding in, and then you want to define a probability distribution which generates new images for you. So this conditional probability is also categorical probabilities. They are computed from these variables X or H. And what we want is now this probability, which is formally defined if these are continuous variables. And this is exactly the same thing which we did with Boltzmann machines. So I'm just keeping this parallel to Boltzmann machines. But then you will see that the variational autoencoders are a little bit more complicated than Boltzmann machines. And then there's an integral of D of H. Alternatively, we can have a discrete one. And if H is a discrete variable, and if this because we can now actually rewrite this one, we can rewrite that in terms of a conditional probability of P of theta of X given H multiplied with P of theta as a function of H of D of H. So now we are simply using the product rule from statistics. And later, we are going to rewrite this in terms of Bayes' theorem. So what you have now is a probability. So if this theta is H is a discrete variable, and this conditional probability is a Gaussian, what happens then is that the final probability will just be a product of different Gaussians. If you have a different set of finite Gaussians, so this P of H here could also just be a uniform distribution. And if you have a uniform distribution, then what you're doing is to multiply this one with a constant. No, sorry, this one with a constant, and then you need a model for these quantities here. So I'm just preparing the ground for the way we are going to actually implement a variational autoencoder. Because if you look at this image here, it looks very nice. It looks straightforward. But we have no idea what this one is. We have no idea what this one is. And we have no idea what that one is. So we need actually to make some models. And that's the whole thing which we are going to, the discussion today are going to rotate on how we actually implement a variational autoencoder. So ideally here, everything looks nice. We have a probability Q of phi, which encodes the data. and it has some parameters phi, as we had for the standard autoencoder, where we had some parameters phi, which could be the parameters of a neural network. And then we have a parameters theta, which then could be the parameters of another neural network. And then we simply train a function where we optimize these parameters. And in a sense, the procedure here is much the same, except that this is not a traditional autoencoder, where these guys here are, for instance, neural networks. And the way we train them is by stochastic gradient descent, and where we end up calculating expectation values, which are then calculated by Markov chain Monte Carlo methods. So what we discussed in connection with Boltzmann machines is something which we can use for variational autoencoders as well. Except that when you look at some of these quantities, if we replace them with a Gaussian, there will be parts which we can calculate analytically. And that saves the day for us and allows us to actually make calculations. So this is a little bit the kind of the setup of what we want. So if we now look at these equations, so we know that these probabilities, the way we have been rewriting them, we know that there's also a probability of theta of h given x. And this is now given by a probability of p of theta of x of h. So this is just the product rule again of p of theta of x. And similarly, we have the other one, which we just used now. So what we are going to do now is to introduce a new probability. So let me just find my notes here. So a variational autoencoder is going to learn stochastically, a stochastic mapping between an observed value, an observed X space, whose distribution, so this is the mapping, whose distribution is something which we are going to call Q of phi, is this Q of phi. And this maps from X to this latent space, H of X here. So this is the mapping which we are going to set up. And this function is normally a complicated function. And the latent, so it learns this mapping between an observed X space, whose distribution is. So this is a model which we are making, and a latent space or hidden space, if we want to insist on the definition which we had for Boltzmann machines, and a latent space H, and whose distribution which is this quantity we called P of H, or the prior of theta, which depends on theta, can be simple, or we want it to be simple. So what we do then is that based on that one, we learn a generative model. So this model learns actually a joint distribution for H going to X, which is the decoder part. So when we've done this encoding, we are then learning a decoder part, which is the one which at the end gives us this P theta of X. So it sounds like a kind of strange circular process here. So if you now look at this distribution, which we had, this P of theta of X of H, this is now given by this P of theta of X of H multiplied with this P of theta of H, which comes from the latent space. So we need to have a model for this quantity. So we need a model. And the normal model is actually to assume that this is a Gaussian. We are coming back to that. And we need, obviously, a model for this quantity, which you have here as well. So what is marked in red here are models which we need to make up. And this Q is also normally given in terms of a Gaussian with parameters which are trained. Okay, so the idea now is that this Q of phi, which we have defined as x of h, is now going to approximate the true probabilities, which maps from x to h. No, sorry, this should be, it's the opposite here. So this is h of x. So we are assuming that there exists a real probability which makes this mapping, but we make an approximation. So this is essentially a model which we are going to make. Okay, so let's go back to the description of what we want to optimize. So from last time, and this is where I'm going to bring back the Kullback-Leibler divergence. So from last time, the thing we wanted to optimize, so we want to optimize then we have these parameters, theta phi, and phi is actually a hidden parameter in this P, but so you can actually have an implicit parameter here. This is the quantity we want to optimize. This is the final probability, and we want to make sure that when we have this P of theta, then we know that the x's we generate are then given by this P of theta of x. So I generate new x's, like I would use a normal distribution to generate new variables. And then I clearly want these x's which I generate to be as close as possible to what we have here. So the training deals with actually us optimizing this probability distribution. So let's go back then. And one of the things we did then last time was actually to find that this log, sorry. So I'm just repeating a little bit from the equation we had last time. This was given by the expectation value, where we now generate these probabilities, these conditional probabilities with h given x. So these are probabilities which are generated in terms of that. So I'm going to bring up why we ended up with that equation. And before we take a small break here, this ended up being given by the expectation value of log of p of theta of x. So let's stop here and take a small break. And then I'm going to remind you quickly about what we did last time so that we can rewrite the optimization problem in terms of a Kullback-Leibler divergence, which we can calculate when we have a model, and then something which we can evaluate by a standard Markov chain Monte Carlo machine. So this is where we will end after the break. But let us stop here now and just take a small break, and then we do the final derivations. Actually, everything here is in the article by Kim and Welling, and you can find all these details if you want to. So last week, this is to a certain extent roughly where we ended last week when we discussed the Kullback-Leibler divergence. I wanted to repeat some of these arguments so that you can see all the basic steps. And what I wanted to do now is just to give you a small intermezzo where we actually look at how we got to that specific equation. So let us just go through those steps. And so let's just bring that as a small intermediate step. So when we look at this log p of theta of x, what we are computing is actually log, and then we have the integral over p of theta, and then we have x given h, and then we have this p of theta of h of d of h. So this is the quantity we're actually evaluating. And this was the same as log, just to remind you of that, of P of theta, and then we had the probability of X and H of D of H. This is just a definition of the marginal probability, which we also had previously. So what we do now is that we simply insert 1 into that equation. So insert 1, and we just put that one equal to this Q of phi of H given X divided by itself. And then what we get is that this log of P of theta of X is the same as log. And then we have an integral over P of theta. And now I'm just going back to this more shorthand here of X of H. And then I have Q of H of phi of given X divided by Q of phi of H of X. And we have a D of H here, like that. And if you look at this one, when we now are setting up the equations, this is nothing but the expectation value. So this is the expectation value. So I have to be a little bit careful here because it has a little bit to do with the ordering of things. But this is nothing but the expectation value of Q of phi of H with respect to that probability, because we have this quantity in here. And this is going to be the probability of log of P of theta of X of H divided by Q of theta of H of X. So what we have then, if we now look at, go back to the equation which we looked at previously. So we, what we did then was to rewrite this in terms of that specific quantity here. And now we can bring back the definitions which we had for the conditional probabilities. So we can actually rewrite this in terms of the probability, and this is roughly where we ended last time. And then I have a log of P of theta of X of H divided by Q of phi of H of X. And now I'm just using these relations between different probabilities. So I have a Q of phi of H of X divided by P of theta of H given X, like that. And when I use that one, I can rewrite the last term as this Kullback-Leibler divergence. So this is the same as the expectation value with respect to this probability H, this conditional probability, which we actually don't know. And this is now the expectation value. So this is just a symbol for expectation value. So that's an integral, which is evaluates this function log P of theta of X of H divided by Q of phi of H with respect to X plus this EQ of phi of H given X. And then I have log of Q. So when I introduce this quantity Q of phi here and have this Q of phi, I was simply multiplying that expression with 1 again. So then I could introduce these quantities, and then I have now a Q of phi of H given X divided by a P of theta of H given X. Now, the quantity you see here is actually a quantity which is nothing but this Kullback-Leibler divergence. So this is what we defined last time as the KL divergence. And we would typically rewrite this term here in terms of a function which we define as KL. And then we have Q of phi of H given X. And then we put this double bar here, and P of theta of H given X. Now, this is the function which we are going to evaluate with the Gaussian distributions, and which is going to give us an expression which ends up being an analytical expression. So the expression which we also have to keep in mind, one thing which we have to keep in mind is that the quantity you see here, you can show that this quantity KL of Q, and I just write it in a short term now, of P of theta. This is a function which is always larger or equal than 0. Yeah? Yeah. So the only thing I did was actually in here, I have this ratio. So it was actually, what I was including in here is just a factor of 1 in there. And then I've been using the different conditional definitions for conditional probabilities. You can actually, if there is some doubt here, you can, let me just bring back again. So the one thing I recommend normally is actually to take a look at the article by Kingma and so what you have is that this quantity here, this is the one which we put up, and then you simply add 1 in here, and then so getting to this equation is the one which I reminded you of, this intermezzo here. So this is a quantity we are evaluating, and then you have the conditional probabilities. So in my case, Z is equal to H. So I kept this connection with the Boltzmann machines. And then I get this quantity here, which is called the so-called evidence lower bound or variational lower bound. I'm coming back to these things here. Oops, where did I put my, here we are. So the quantity which we want to optimize now when we are calculating derivatives is this quantity which you see here, plus this quantity here. So again, this looks as something which is just intractable. So how can we actually do anything with something where we have no idea what this Q looks like? We have no idea what this P of phi looks like. So the question now is, how can we actually do anything at all? So if we look at the equations here, so the first term, which you have, is normally called the variational lower bound, or the variational bound simply, or it's called the evidence lower bound, because since this quantity here is either larger than 0, or it is exactly 0 if this probability here is the same as this one. Then it's exactly equal to 0. So the Kullback-Leibler divergence is always a quantity which is larger than 0. So when we are performing this optimization, we know that this is the kind of variational lower bound on the calculations. So the first term, let me just write this down. So the first term is normally called the variational lower bound. Or, as you will also see in the literature, it's also called the evidence lower bound. I prefer normally variational lower bound. And it's normally shortened to ELBO. So what you can do then is when you look at that specific quantity, the quantity you then want to optimize would be a function of x, which is actually this specific expectation value of q of phi given x. And then we have a log, the expectation log of value p theta of x of h, which we then are going to rewrite later. So this is a quantity which is given by p theta of x given h, multiplied with p theta of h. And then minus, and then I have log of q phi of h given x. So that's the expectation value. So since this KL divergence, this Kullback-Leibler divergence is 0 or larger than 0, then optimizing that specific function is the one which plays the major role when you're performing the calculations here. So you should also keep in mind now that in the optimization part itself, this, when we take derivatives with respect to phi, then this function here is independent of, with respect to theta, this function here is independent of theta, which means that the derivative of this quantity here with respect to theta contains only this term. And then similarly, when you take the derivative with respect to this parameter phi, this term here does not depend on phi, but then it will be this term here, which is the one which becomes important. So the this kind of KL divergence, which we also have, this quantity here, that defines two kinds of measures. So one is the approximate posterior probability from the true posterior, which is this one. So this is then the posterior probability we want to define. And if there is a true one, so this would define a measure of the difference between your model and the true one. And then the gap which you have from this function which you see here, the difference there, that defines the gap between that function L which we have here and the marginal distribution. So maximizing this function here, this is what we typically end up with respect to theta and phi, then will approximate this x, and it will also give us the final probability. So the generative model gets hopefully better when we repeat the different optimizations of that function here. And it will typically minimize also this Kullback-Leibler divergence of this approximation Q of phi from the true posterior. So one important property of this functions which you see here, in particular this function, is that it allows joint optimizations with respect to all the parameters. So you would have an optimization with respect to both theta and phi when you look at this function which you have here. And same with the Kullback-Leibler divergence. So the problem is that, as I said, to calculate the derivatives or the gradients with respect to this function phi is something which can be pretty tricky. So how do we actually do this? So let's look at the graph first on what the machinery is going to look at. So the computational flow of the variational autoencoder. You can now think of you having some data points, some image, X, and this could be an image which you're feeding in, some mountains in the background, some happy person on a sunny day. So this could be the image you're feeding in. You can see my artistic skills here in full expression. And then we would now have some kind of inform or inference model, or the decoder, or the encoder. And we are now mapping, so this is our axis. we are mapping this to a latent space. And we produce a sample for H with that. So this is the latent space. And then this creates this is the decoder part. So that gives us a generative model. And that gives us a P of X with a given H. So this is the decoder part. And all these guys here, they feed into what we will call the objective, the final objective. Which is the optimization of this function. And I'm leaving out the Kullback-Leibler, and I'm writing this in a more compact way of X of H minus log of Q of H given X. And this expression, which you see here, is the expression for this specific function without the Kullback-Leibler divergence, which comes in addition. So this quantity here is the one we want to optimize. So this is the objective function, which we now want to optimize in the procedure, in the variational autoencoder. So the Q of phi, which we have, we can just wait a little bit so people can write it down properly. So this function Q of phi, and I've taken away some of the subscript here, but this function Q of phi of X of H is something which we can define as an intermediate step and defines the encoder. So the some of the quantities which we then want to evaluate, so if we look a little bit more carefully at it, so let me just bring back the right notes which I wanted to have. So what we have is an EQ of phi of H given X, and we found that this one is equal to the expectation value of Q of phi. Let me just rewrite this one a little bit carefully here. So this is given by the expectation value. No, wait, just a moment. So let me rewrite it a little bit more. So we have a log of P theta of X of H divided by Q of phi of H of X. And that is equal to the expectation value Q of phi of H given X of log, and now I'm using the standard definitions of from the product rule for probabilities of P of theta of X given H of P of H divided by Q of phi of H given X. And this, so I'm taking away the Kullback-Leibler divergence. And then I have Q of phi. I just shorten this one like this. So I have a log of P of theta of X given H plus the expectation value of Q phi of log, and now I have P of H. So this has a parameter theta divided by Q phi of H given X. And this is something which I then can actually rewrite in terms of a new Kullback-Leibler divergence, because this quantity which you see down here is something which I can rewrite in terms of the probability of H. So I can actually rewrite this one as a Kullback-Leibler divergence. So this is given by E of Q of phi. And then I have a log of P theta of X of H minus, and this is the Kullback-Leibler divergence of Q of theta of H with a given X. And then I have this double bar to indicate the notation. This is the notation for the Kullback-Leibler divergence, like this. So these terms have a different meaning. So the first term measures what's normally called the reconstruction probability of the decoder from our variational from our distributions. And the second term, that measures how similar the learned variational distribution is to a prior belief. So the first term measures the reconstruction probability of the decoder from our variational distribution. And the second one is normally called a prior matching term. And the question now is, even if we have these equations here to calculate, how do we actually proceed? Now, this term which you see here, this is normally estimated with a standard Markov chain Monte Carlo procedure. So the first term is normally solved with a Markov chain Monte Carlo procedure. So Markov chain Monte Carlo. But then the question is, how do we actually calculate the second term? So how do we proceed with the second term? So an important feature of these variational autoencoders is this variational lower bound and how it's optimized jointly over this variable phi and theta. And the encoder part of the variational autoencoder is commonly chosen to be a multivariate or multivariable Gaussian distribution. So the common choice which you will encounter when you look at these variational autoencoders is to take this function Q of phi of H of X to be given by a normal distribution as a function of H. And then it has a mean value, which depends on parameters phi, which is then optimized as a function of X. And then we have in addition a variance, which also depends on some parameters phi squared of X. And this is a diagonal covariance. So that means it's just multiplied with the identity matrix. So this is a very common approximations because that allows us to calculate this quantity here analytically. And that means that you can also take analytic derivatives. There's something which is called a trick, which is called the reparameterization trick, which I'm going to describe pretty soon here. But the whole thing is that by making this choice or a choice in terms of known probabilities, then you can find an analytical expression for that one. Then the only thing you need to do from a computational point of view is to perform a standard Markov chain Monte Carlo sampling of this expectation value here. Because this quantity here is something which you then can define in terms of the Markov chain Monte Carlo calculations. So let's take a closer look at the next thing. So this quantity here needs also to be defined. So this P of H of theta is also normally given by just a normal distribution of H, zero mean value, and a variance, which is just 1. So this is the mean zero, mean value. And this is the variance. So that means that we can compute this KL divergence the KL divergence analytically. And this reconstruction term is normally approximated with a Markov chain Monte Carlo. And the first term, which also is called the reconstruction term, or the reconstruction, is estimated by Monte Carlo sampling. So what we did for the Boltzmann machines, the optimization of a Boltzmann machine, something which we can repeat and apply to variational autoencoders as well when it comes to that specific part. So what we end up with then is the following problem. So we have a maximization with respect to these parameters, which define the encoder and the decoder. And we have then the maximization of the distribution log of P of theta of X given H minus the divergence, the Kullback-Leibler divergence with respect to something which we can define in terms of analytical functions. Now, the calculation of these derivatives normally leads to the following. So that means that when we do this in actual calculations, this is the same as argmax theta of phi, and then we have a loop over the number of Monte Carlo cycles or Monte Carlo samples, so MCS, Monte Carlo samples. And then we have a sum of I equal 1 up to the number of Monte Carlo samples. And then we have a log of this function of P theta of X given an H of I minus this Kullback-Leibler divergence, which can then be calculated analytically with a model. So the latent variables, just to say that, the latent variables H of I, they are sampled from this model which we have, from Q of phi of H of X for every observation which we have. X in the actual data set. Now, there's a problem now, and that this H of I, which you see, is generated by a stochastic sampling procedure. So you have the input data X, you have made a model here. And that means that when you look at these variables H, they are actually generated by this sampling from Q of phi. And this sampling procedure can actually be difficult, the variables you obtain can be difficult to differentiate. So what is commonly done then is to reparameterize the variables X and the variables H in terms of some simpler functions. So just to keep in mind now, when you look at these variables which you produce here, they are now generated from a normal distribution. And this means that when you now are plugging these into this equation here, sometimes this can actually lead to problems, or since these are stochastic variables, it can lead to quantities which are difficult to differentiate. So what is common then in the variational autoencoder machinery is actually to reparameterize. So we can reparameterize. It's called the reparameterization trick. Reparameterization trick. Trick. And what you would do now is to rewrite. So this rewrites a random variable, a stochastic variable. As a deterministic function plus some noise. Deterministic function. Function of a noise variable. So that means that X can be drawn from a normal distribution with X with a mean value and a variance sigma squared. And you would then add some kind of noise. So you would have A. So instead of having this distribution, you would rather have X as a function of mu plus some sigma times epsilon, where this epsilon is drawn from a normal distribution with zero mean and variance equal to 1. And so that means that when you do this in a variational autoencoder, so this is just general variable X, but in a variational autoencoder, what you would do then is that this H is now equal to mu of this phi of X plus sigma of phi of X multiplied with this epsilon. And where this epsilon is generated according to a noise model. And when you're calculating the derivatives of these quantities, this noise doesn't appear. So in other words, what you're doing now is to have arbitrary Gaussian distributions, which can be interpreted as standard Gaussians, of which this epsilon is just a sample, that have their mean shifted from 0 to a target mean by addition, and their variance, which is stretched by the variance sigma squared. So by this reparameterization trick, what you're doing now is to sample from an arbitrary Gaussian distribution can be performed by sampling from a standard Gaussian and scaling the results by the target standard deviations and just shifting it by the target mean. So in the variational autoencoder, each of these latent variable H is computed as a deterministic function of an input X and an auxiliary noise variable epsilon. And after training via a variational autoencoder, you're generating new data, can be performed by sampling directly from the latent space, probability P of H, and then running it through the decoder. And the variational autoencoders, they are particularly interesting when the dimensionality of this latent space is much smaller than the input space X. So if you go back to the discussions we had of a standard autoencoder, one of the features of a variational autoencoder, which is similar to a standard autoencoder. So if you think back to what we put up here, so a standard autoencoder has normally a latent space, which is designed to be smaller than the input space. So this is where you would have the dimensionality reduction. So when you come to the variational autoencoder, the idea there as well is to have a small latent space with, compared with respect to the input space. This is also similar to what you would have with a Boltzmann machine. So if you go back to a Boltzmann machine, you can have many visible nodes, but you would often try to limit the number of hidden nodes. So I'm trying to keep this kind of comparison with the different methods. So this kind of latent space, which follows from the encoder to the latent space and then back to the decoder, the whole philosophy is to try to have a small space here. small number of variables compared to the input space. And the input space could be a big image, and then through the encoder and the latent space here, you can then reconstruct the decoder, which then leads to the final probability P of theta of X. Hopefully, by going through less steps than you have what from the input data. So one thing, if you now are looking at how to implement this, so I'm going to switch a little bit. And I wanted to bring up the article by, it should be this one. So if you go into the article by Kingma and Welling, after all these discussions, or many of the things which I mentioned are the same as those which you saw on the whiteboard here. You will also find the discussions on how to perform the optimization. And if you scroll down, and if you want to implement this, there is a pretty detailed description of the algorithm for the optimization, the stochastic optimization of this variational lower bound, given you having used a Gaussian distribution. And you can see all the kind of small technicalities which we will not cover, mainly due to time. But you can, if you want to implement a variational autoencoder, there is actually enough description here in the article by Kingma and Welling, which should get you started if you want to do that. And there is a detailed description on how you calculate the gradients and how you perform the optimization. And there are well-defined pseudo algorithms. So if you would like to code yourself some of these generative models, I think seeing the time which we have at our disposal, the simplest one to code is actually the standard Boltzmann machine. The variational autoencode itself, I believe, would be something which could be more like a one-semester project. So even if I suggest writing a code for a variational autoencode, I think this would be a little bit too lengthy. It would require a little bit too much time. So I would, going back to the project which we have, I would rather suggest that if you want to code this yourself, as a part of project number 2, I would focus on Boltzmann machines. Although Boltzmann machines have been superseded by variational autoencoders and diffusion model. The problem here is that you have a little bit more tricky functions to optimize, and it's not given that you will, within the time which we have, roughly less than 2 months, that you will actually be able to write a decent code. So that was for one of the variants of project number 2. The other variants are obviously based on you utilizing code which you have in TensorFlow. And in the lecture notes, there are examples of both PyTorch implementations and TensorFlow implementations if you want to use variational autoencoders. Similarly, we also have codes for general adversarial networks, which is something which we will discuss a little bit more next time. And also next time, which will be basically our last lecture like this, I'm also going to mention diffusion models. And you do have actually through the textbooks, which we have linked up here. So let me just bring back some of these textbooks in the project. They're also in the project description. So if you go to the project description, you will find codes for energy-based models in chapter 7. If you want to code variational autoencoders or use TensorFlow, Foster's textbook actually has examples of that in chapter 3. And then finally, for diffusion models, you will find several TensorFlow examples in chapter 8. And the textbook by Babok and Bali, which we have also been mentioning, has in chapter 4 quite a good description of how to use TensorFlow to set up a restricted Boltzmann machine. And that is actually this code which you see linked here. So there should be enough examples, but if you want, as we have in the project here, if you want to code a Boltzmann machine, this is something which I think could be doable. But I wouldn't recommend, unless you have quite some familiarity with variational autoencoders, I would not recommend coding that as part of project 2. So as I said, there is a variant where you can write your own software. But for generative models, the easiest way to get started is actually to implement a Boltzmann machine. Okay, so next week, I will run through general adversarial networks and say something about diffusion models. And that will be essentially our last lecture. And then from then and on, in May, till the end of May, we will just have lab sessions here. So feel free to come then and then discuss the projects with us.